I put this together mainly based on some experiments I've done over the years, just because I was curious, kind of the thing Craig was talking about. And this is another one of those things that's a huge topic. I mean, you know, you could talk about this for hours and hours, but we're not going to do that. So, we're going to look at designing a tuned small signal high frequency RF amp. We're going to use LC circuits to get some selectivity and some gain. We're going to try to match the active devices, the output impedance, the input impedance, get good gain. And like most things, you can't have your cake and eat it too, so you can either have a lot of gain and not a lot of selectivity, or you can have a lot of selectivity and not a lot of gain. You can also design maybe for best noise figure, but you're not going to get the best gain. I don't think that's ever going to happen. So everything's a compromise. You got to kind of decide, what am I after, what do I want to do, and then concentrate on that. It seems to me in the literature I read these days, people are doing things a little differently than I'm going to show you. I think the kinds of things you're going to see here are more from the DeMaw era, but I kind of like building stuff like this, so I tend to do it this way. We got to pick a device. I don't know, 3904, 2222, any of these will work. Got to have some DC bias. These are going to be Class A small signal amps. I just picked a milliamp. That's what I usually do when I'm doing these experiments. Coil type. Lately, I've been kind of headed more towards slug-tuned coils because I like the ability to adjust the inductance to a real fine degree. But a lot of these experiments were done with toroids as well. We need some idea of how much gain or selectivity we want. And what I'm going to show you is something that works well for me that's kind of a compromise. You get decent gain, you get predictable selectivity, and if you need more of either, you just have to build more stages. So here's the tank. With an inductor, capacitor, we're going to use a parallel resonant tank, and that R sub C is the loss in the tank. In other words, you could hit a tank like this with a pulse, and if it were perfect, it would just ring infinitely, forever. But every time current makes a trip around the tank, we lose a little bit of energy, and that's what RC is representing. And at high frequency, most of that loss, or maybe almost entirely, is in the coil, except when it isn't, and we'll talk a little bit about that later. Resonant frequency is 1 over 2 pi square root LC. X sub C is reactance to the cap. X sub L is the reactance to the coil. And that FR X sub C is going to equal X sub L. Q. You guys remember the lame guy from Star Trek who played Q? You know, I saw him in a Shakespearean play at the Ordway once. And I always thought on Star Trek he was just a doofus. Yeah. But this guy really can act if you give him a good role. I don't even remember his name. But anyway. One definition of that is the ratio of the amount of power stored in either the coil or the cap to how much is dissipated or lost. Selectivity and Q are intimately tied up together. And for the type of amp we're discussing here, we would like a high Q. So we're going to work towards obtaining that. Can also be defined as X sub L or X sub C divided by RC, which is the loss. So to get a high Q, we want to use a large value of X. More turns on a coil typically yields more X sub L. The loss goes up as well, but typically not as fast as the inductance or the reactance, at least to a point. Now, I think I mentioned in one of my other presentations, when I was a kid playing with some of this stuff, I used to try to do things like, I'm going to build a 100-watt crystal-controlled oscillator, and it's going to be a single stage, and it's going to run off a 9-volt battery. You want a lot of Q? Let's use a 10 Henry coil. Well, you know, it looks great on paper, but it's just not going to work. So you got to use reasonable values. Well, a lot of my experiments around 14 meg tend to use something around a 2.6 microhenry, and that requires about 50 picofarads to resonate at 14 meg. You get below that 50 puff value, and the stray capacitance starts becoming most of your capacitance, and you have a hard time tuning your circuit. So I try to stay around these values. Depending on what calculator you use, that's either 23 or 24 turns on the T50-2 toroid core. Try and stay away from core selections that call for either very few turns or many turns, because we're going to need some room on this core to work, and we're also going to need to do some tapping, and when you only have a few turns, your options are really limited. Fatter wire will typically result in lower loss, but we need some room. See, again, it's a compromise. So back to this tank we're going to use. 2.6 microhenries is about 229 ohms of reactance at 14 meg. And I've run a number of experiments on this, and at least for the coils I'm using, I get a value of about 1.2 ohms for the loss. And that's not something you can measure with an ohm meter. I wish it was. It'd be a lot easier. But at high frequencies, skin effect and core loss, it's going to be more than what you measure with an ohm meter. So let's see if we can figure out what the Q is. Well, the Q is going to be the reactance divided by the loss, which is 191. Let's call it 200. And we're going to round off a lot of these values because a lot of this stuff is close, but not exact. This value is sometimes called the unloaded Q, or Q sub U. It's basically the Q of the tank with nothing hooked to it, just the tank components itself. The bandwidth for selectivity of that combination of 14 megs and 200 for the Q is going to give you about 70 kilohertz. The impedance from the top to the bottom, which is going to help us determine how we hook our devices up, is going to be equal to Q times X. So we got 200 exabella, or no, 200 Q and 229 exabella, so we get about 46K. Higher Z tanks can provide higher gain, but again, don't get carried away. You'll run into all kinds of problems with stray effects. Cloud goes over, things change. It's not worth it. So now we're going to build up an amplifier. We're going to build up a two-stage amplifier, and you'll see that you can extend this to more stages using a tank to provide gain and selectivity. And we're going to use that good enough compromise that I talked about. And that involves loading or connecting to the tank the output of stage number 1 and the input of stage number 2, such that stage 1 loads the tank with a value equal to the impedance of the tank, as does the input of stage 2. And that way we're going to try to match the two devices to get the best power transfer. And we're going to do that using taps on the coil. Now you can also, instead of taps, you can use links. Like if you want to tap at 2 turns, you could use a 2-turn link. What I don't like about links are that the core starts to get full of wire and you can't tell which lead is what. And the other thing is, even with toroids, you don't get, at least I found a lot of times, you don't get the same amount of coupling with a link that you will with a tap. Little, you got your core and you got your main winding. Right. You'll take another piece of wire and wrap a couple of turns. Independent. Yeah, independent. Right, like a secondary winding. So here's the schematic of this thing that I built up. Some of the stuff is the same stuff you'd see at DC. We got our biasing resistors, and we've got a decoupling resistor up here to keep RF out of the DCC so it doesn't end up talking to other stages. Bypass cap up there. And then we're going to tap the collector of this guy into the coil, and we're going to tap the base of the second guy into the coil. And you'll notice I've got a variable cap in there. We're going to talk more about that a little later. But as I mentioned, I'm starting to get to the point now where I like to use slug tune for a couple of different reasons that we'll talk about in a minute. So, first approximation, signal levels, frequencies we're talking about. You can consider the output impedance, the collector output impedance of stage number 1 to be equal to VCC, in my case 12 volts, divided by IC, which is 1 milliamp. So you get 12K. First approximation, Zn of stage number 2 is going to be equal to little re times beta at FR in parallel with these two guys, but these two guys are so big that we'll just ignore them. And the little re is the emitter resistance of the device, and that's generally calculated by taking 25 millivolts, which is a constant, and divide it by your emitter current. So little re is going to be 25 ohms. Beta is same thing as HFE, and you can get that off a spec sheet. We're going to assume for this one it's about, what did I get for that? Beta is, oh yeah, at FR is the FT, which is the cutoff frequency. That's the point where beta gets to a value of 1, divided by whatever frequency you're working at. And if you take a 200 megahertz FT, which is pretty typical for a 2N3904, and divide it by 14, you get, not by 14, I'm sorry, well, yeah, 14 megahertz. You get about 14. The beta is about 14 at that frequency. So, let me go back on here for a minute. Remember how to go back. There we go. Lost my train of thought, which happens when you get old. Zn of Q2, using that technique, comes out to about 350 ohms. I'm going to talk a little more about that later, in that that's probably one of the numbers in here that is the most uncertain or variable. So we want to match the output impedance of Q1 to the input impedance of Q2. So we want to match that collector impedance of about 12K to the input impedance of that second stage. We're going to do that with a tap, and we need a tap that's going to transform 48K or 12K to 48K, and that's a ratio of about 4. Well, impedance is transformed by the turns ratio squared, so we're going to use a 2-to-1 turns ratio, and that'll give us an impedance ratio of 4-to-1. Well, there's 23 turns on the coil. I don't know how you do a half-turn tap on a toroid, maybe you can, but I just tapped it at 12 turns, about 2-to-1. And then we want to transform that really quite low 350 ohms Zn of Q2 to match the 48K impedance of the tank. To do that, we use another tap. Well, 48,000 divided by 350 is 137. Again, impedance is transformed by the turns ratio squared. So a 12-to-1 turns ratio gives an impedance ratio of 144-to-1, close. 23 turns on the coil, okay, we'll tap at 2 turns. So now you've got a tank that has a impedance of 48K due to its internal loss. The output impedance of Q1 has been stepped up to 48K across the tank. The input impedance of Q2 has been stepped up to 48K across the tank. This should match the output of Q1 to the input of Q2, which at least with BJTs will give you maximum power transfer between the two transistors. So what effect does that have on the Q and the selectivity? Well, the tank now has 3 sources of loading, or 3 loss sources, which determine its loaded Q, or Q sub L. It's got its internal loss. It's got the transformed impedance of Q1, transformed impedance of Q2, and assuming they're all exactly 48K, comes out to 16K. This is 1/3 of the unloaded value, and this is the compromise I was talking about earlier. You don't have to do it like this. You can transform your impedances to a different value, but the selectivity, the gain, and the loss are all a compromise, This is an easy way to get a little bit of everything, but it isn't the only way. Another way of looking at that would be to think of the tank having nothing connected to it, just back to the coil, the cap, and the internal loss. But that internal loss being 3 times higher than it was before. Well, in the unloaded case, it was 1.2 ohms. So for the loaded case, we're going to call it 3.6 ohms. The Q, loaded Q in this case, will be 229 to X of L divided by 3.6, which is 64. It's a lot lower than it was before. And the bandwidth, again, will be the resonant frequency, 14 meg, divided by the loaded Q. We have now, instead of 70 kilohertz, about 219 kilohertz. It's broadened that response out. It's not exactly 3 times the unloaded bandwidth, because we've been rounding things off, but it's pretty close. Well, this guy, as I mentioned before, the input impedance of this guy, it really gets ugly sometimes. Like, I've had experiments where I'm, chugging right along, everything's working good, and it turns out I need to tap my coil at like 1/10 of a turn because that impedance is so low. Well, you're not going to do that. Rather than go back and start redesigning everything, you can do something like this. You can leave the DC emitter resistance the same. It was 100 ohms before, it's still 100 ohms now. But you just split it up into 2 pieces, and you put an AC bypass across one. The effect of that is now the input impedance of Q2 is now going to be little re plus that 50 ohm value times the beta at the resonant frequency. And in this example, that takes it up to about 1400 ohms instead of, what, 350, I think. Now, you're going to lose a little gain because if you have a fully bypassed resistor, you get the highest gain. Here, we haven't bypassed it all. But, again, everything's compromised. So I've done this many times, and you can juggle those values. It doesn't have to be half. It might be 75 ohms and 25 ohms. Tweaks. Bringing one or both of the taps closer to the cold end of the tank. Cold end of the tank is up here. This is at RF ground via that. So if you move those taps closer to the cold end, you'll get better selectivity. You're not going to load the tank as much, and that bell curve is going to close in, get sharper. But you're not going to get as much gain. On the other hand, if you bring the taps higher on the tank, you're probably going to get more gain, but you're going to significantly widen the bandwidth. If your goal is best noise figure, well, good luck. I found that a real tough nut to crack. And at HF, we really don't need real low noise, but be aware that you're probably going to have to design for best noise figure and take whatever gain and selectivity you get. That analysis that we just went through assumes a very low value of Miller capacitance from collector to base. As frequency of operations increase, these kinds of tools kind of fall apart for a lot of different reasons. I've done things like this up to 10 meters, and it works fairly well. It does work better if you use a better or more high-frequency rated transistor, like a MPS H11, I think, is a 800 megahertz FT, as opposed to about 200 megahertz for a 2N222. This is what I mentioned earlier. All of the loss is in the coil except when it isn't. All caps are not created equal. Some have a significant loss at HF that can really degrade the Q. Some of these little plastic variables that you see, they're kind of a circular shape with a flat on one side, and some of them are blue, red, yellow, different indicators for their value. some of those have a lot of loss, especially if you tweak them a lot. And I tend to do that because I'm always trying to look at things and change things. You can really end up with a lossy component. Those Varicons or polyvaricons that you used to see in AM radios, you know, that now are in a lot of these little tiny tuners, typically they are atrocious. They got a lot of loss. Now some are better than others. And sometimes you don't care. Or sometimes you're willing to take it because it's small. Air dielectric with ceramic frames are typically much better. And they're also, at least new, or maybe new old stock, they're also very expensive. You'll always see me at Hamfest looking through boxes for these little variable caps. Name brand ceramic fixed values, COG types are also typically very good. And especially if you're going to build more than one stage. Murphy's second corollary says if you try to build an amplifier, you're going to end up with an oscillator. And if you try to build an oscillator, you're going to end up with an amplifier. So feedback, either through poor layout or this internal capacitance, can ruin the amp. Especially at higher frequencies, you may have to start feeding some of the output back to the input in the right phase to cancel that feedback. It's called neutralization. And this is a starting point. This is not the end all, because unfortunately the beta of a handful of, say, 2N3904s, it can vary widely. And that factors into the input impedance of that Q2 stage. So you may have to do some putzing. You can change the DC bias point, which is going to change that little RE value. You can change the position of the taps. You can maybe try to wind a higher Q coil. So if you've got a real need for a specific value of selectivity, at least with BJTs, you're going to probably have to do some pivoting. And more stages mean more selectivity and gain. Better be conservative in your designs. None of this I want razor sharp selectivity and Mongo gain with one stage. It's just not going to happen. FETs, JFETs, MOSFETs have some real advantages, especially at HF. The input impedance is typically much higher and easier to work with. And I do a fair amount with FETs, but a lot of stuff I build is still BJT. Double-tuned interstage networks where you've got a tank connected to the collector of stage 1 and another parallel tank connected to the base of stage 2 with appropriate taps, and then the two are inductively coupled together. You couple the two coils together, can dramatically increase the selectivity, and it also becomes kind of a nightmare in terms of design. And it's one of these things where, oh, I'm changing this, things are getting better, now I'm going to change this, oh, things just went to heck. Why? Well, and there's all these variables, the coupling, the tuning, the loading. It's great if you can get it to work. That's about all I got. Questions? Yeah.
What do you do with all these amplifiers you built?
Most of them end up, like most of my projects, on the shelf, and I go over a year later and, what is this? What was I doing? They usually just end up being fun to build, check out.
Okay.
That's about it. Now, sometimes I'll build something complete and use stuff like this. But
you talked about, instead of using a toroid,
yeah,
using a variable inductor like a slug tune.
Yep.
So when I was going to school, we didn't do anything with toroids. It was
Me
all
neither.
slug tune.
Yep.
Where do you buy a slug tune form these days?
Hamfest.
Oh.
I just
Okay.
bought some at Rush City today.
I was going to ask the same question in trouble.
Yeah, because
That's useful too.
I've got an oscillator that I would love to put in a slug-tuned coil, and I've been looking around and I haven't really found the form that I want.
I don't think you're gonna dial up the DigiKey page and find
No,
them, no.
they don't have anything like
No.
that.
I mean,
I've seen them somewhere, I wonder if it stands apart.
yes, he does have some on occasion,
Yeah.
but he's figured out how hard they are to get now, so his prices have gone up. So today at Rush City, I got 4, I think they're 3/8 inch diameter slug-tuned coils in a metal frame. And I think they're a type 2 core, so they're good for HF, for 50 cents.
That's a good deal.
My kids, when I pass, they're gonna go in there and they're gonna say, what, he's got hundreds of these. What are they? Because I buy them whenever I find them. Yeah,
Well, is anything like, a free spice program, where you can maybe compare architectures? You're using common emitter mostly, right?
yes,
And then there's common base, which
Yep.
is good for low noise figure, I think.
Yes.
I don't know about our coupling and interstage and stuff like that.
common base is very good. I use a lot of that for front end stuff.
Yeah,
The downside is the input impedance is even lower typically.
I guess that's right, because it's coming in.
Yeah, and it's tough to match, but the same kinds of principles, yeah, apply. Yeah, common base is great, and they're more stable.
Can you use spice to, get through some of the,
You know,
boilerplate on these things?
I have done some simulations. I don't do a lot of spice. I don't trust a lot of the results. And I know, and I'm being perfectly honest, I know part of that is because I don't know how to use spice well enough. The other thing that turns me off about spice is I work with a number of engineers every day, and that's all they do. And then I build stuff for them, and it doesn't work the way they think it should. And they say, no, you built it wrong. And I said, no, I built it with real parts instead of, I haven't done much with it, but I'm maybe,
Got its place.
yeah, it does. I think you're right.
Some spice programs can do like Monte Carlo simulations.
Yeah.
Yeah.
There was a program out, the ARRL sold it a number of years ago called Radio Designer, and it was like a incantation of spice, but it had, in my view, a much friendlier user interface. I think it was about $150. I got a copy of that, and I did a fair amount with that, and I liked using that one. But it came on floppies, that tells you how old it is.
5 1/4 or 3.5?
3.5. It wasn't bad.
Well, I got into spice really early, because, we had, our computer architecture people on mainframe.
Yeah.
They were actually beta testing the stuff out of Berkeley. And I sit next to them, and they didn't know much about circuits, and I didn't necessarily know that much either, but I was able to look over their shoulder, and I thought, it's kind of neat.
Yeah.
And then I got pretty good with H-Spice, because we go on CMOS.
Yeah.
Not to really simulate that, but when I went to the graphical thing, where you could build your circuit, and then it would give you a net list,
Yes.
that was really the worst, because it would scatter stuff all over, and you couldn't find your block, like your stages one by one.
Yeah.
You'd like to see it. The parts are all in that one stage. It just scatter resistors here and there and stuff. It's probably better now, but I like the old text.
The command line like
Just
interface?
text input, because most circuits aren't that big.
No.
You can put in most circuits in an hour or something. Just type it.
Yeah.
I have to say, I did this complete thing in LT Spice before I built it.
Yeah?
We did.
The whole receiver is in LT Spice, and it shows all the gains through the stages, the whole
Yeah.
works. And the transmitter too, but that was more than a single generator and some gates, so it was so simple, there wasn't much there, but
Yeah.
otherwise, all Spice. I mean,
Did you get 1-to-1 on that?
1-to-1.
I mean,
Did it agree?
it functions the same as.
It's pretty close. I mean, I could look at different stages how much gain I was expecting out of this op amp and this, and I added them together and just put exactly what I got. I have 105 dB of gain in the audio section, and that's just about exactly what the thing told me. So, I mean, I happen to have the right parts. I happen to have the 905532 op amp model for it. So I was able to plug it in there and put the rest of the pieces through with some assumptions, but yeah, it really.
I think that's the other thing, models have gotten a lot better.
LT Spice is free and it's incredibly good. Good support, good, try it. I mean,
What's your front end in that receiver?
SI 570.
What's the mixer?
Oh, it's just got an ABE1, which is a diode ring mixer.
Oh, yeah, okay.
ABE1 is a package, so I don't have to worry about
Yep.
individual ones and they'll match.
Yeah.
So,
Some mini circuits?
Yep.
Yeah.
yep.
I love
got a whole
mini
string of those things out at Dayton one year.
Yeah.
So,
Yeah, thank you.
yeah. So, yeah, it's LP Spices. Rick, my friend Campbell up in Oregon, and professor at WE, used the LP Spice in all of his classes, and he says the biggest experiment is to get the LP Spice to match the model. And then he said, and he goes back and has them change the model to add in stray capacitance and change it, trying to see how close he can get it to match up.
Yeah.
And that's where they learn a lot.
Yeah.
Because you're absolutely right, you can't, for all peeves, the guy used to hate spice because people depend on it too much and assume that it's always correct. So you have to know what you're doing and what to change to make it modeled properly.
Well, and you have to be able to recognize when you get an answer that's like,
Yes,
no,
it's not-
that's like,
But I used it at work too. I had to design some oscillators and some specific pulse width and all that kind of stuff. And I was able to put it to spice, come up with some values, build it in the real circuit, and boom, they were right on. So, I mean, it is place. It works fine, but it's, you have to have all the warnings before you get to it. So.
yeah, the thing I found with a lot of the people I work with, and frankly, they're much younger than I am, and they're all very fine people, but most of them didn't spend their late childhood and teenage years building stuff and blowing stuff up and, finding out what this is and why that didn't work.
I always thought it would be fun to sometime do a presentation here even. Make an oscillator, show how it works in LP Spice, measure the real thing and see how they that kind of thing.
I think you just volunteered.
Well, I don't know. I'm not sure. Once again, I didn't know how much interest there would be in it, that kind of thing. But, I mean, it's certainly, I mean, looking at an oscillator from all these different perspectives, for example. Look at it in the scope, look at it in LP Spice, look at the circuit and what it does.
We've never been told that a presentation was not of any interest to anyone.
Well, no, it's not, it might be out in the weeds for a lot of people, but I mean, it certainly is a possibility. And,
LT Spice, free?
yeah, absolutely free. Like, Linear Tech put it out, so that's what LT stands for. But so they have all the Linear Tech parts there in a huge catalog. The other parts have been added by people, but you can add a model real easily. So you get all the other varieties too.
Another one called NG Spice.
Is that right? Okay. I just have been very impressed when they draw the graphs, and when I want to illustrate something, I put an LP Spice and try it, and it's just a powerful tool.
If we ever lose the grid or the society collapses, we're going to lose an awful lot of stuff. A lot of knowledge and...
You do that in Explorer? Do you use Spice?
I'm the only one in my
really?
class who uses that. We have, on campus, we have multi-sim.
Oh, yeah. Once again, that's a costly one, though, and there's a yearly subscription and everything, but it's a wonderful,
That's a national instrument.
no, is it? Oh, they bought that, that's right. So, yeah, but you would pay for that one, so.
I think you can get a free
Version?
copy, hobbyist copy,
that's right.
through Moser or Newark or somebody. They partnered up with them.
Yep. I used to use a bunch of those old versions too, and I compared them and had 3 or 4 different versions that I've used also. And until I came up with, the LP Spice, I just kind of standardized instead of trying to switch gears all the time. And everything I do there's a million ways of going about it. I tried to try and solve it because you'll know how to switch from one to the next and the detail.
Okay,